Okay. All right. All right. Can you hear me clearly at the back? Okay. Thanks for hanging on here. This is work on how to search and retrieve in the era of LLMs. This is work with, or work by a lot of excellent collaborators. I'm just the messenger. So before continuous embeddings, or BCE as we call it, text indices used to depend on discrete word-based lexical entities. And they used to, every word would map to an inverted index which would contain the IDs of documents that contained those words. These were discrete indices and could be optimized for millions and billions of documents, but they were not as high quality as indices later built using deep learning methods. High quality in the sense of recall. So if you ask about a panther, maybe some document having wildlife or leopard should also come in, and that didn't used to happen sufficiently. Then in 2013, around, something magical happened. Word2Vec and GloVe, the word embedding technologies were invented, and the rest is history. So AD is like after DeepSeek or after DeepMind, semantic indices started getting built using these continuous embeddings where every word would become a vector of say 500 or 768 real numbers. And it's not just language. We could do this with audio, images, video, and so on. So multimodal search also became a reality. And to search these vectorial objects, we needed vector databases. And those use technologies such as locality-sensitive hashing and hierarchical search structures. So all this is well and good. To start the talk, I'll give a 1-minute primer on how text encoders work in the era of large language models. So a dense encoder, which might be a transformer, it might be some other kind of neural network, inputs a text like this. You start with a special token called a CLS token, which is reserved, and then the sentence. He swam near the bank because the current was swift. And the second sentence is his bank offered a low interest on current accounts. Now, when this passes through the encoder, although the word bank is shared between the two sentences, at the output position, bank 1 and bank 2 would give very different vectors because the meaning of bank is very different in the two sentences. Now, a vector is output for every word in the sequence, and a vector is also output for the CLS token on the left. You could use either or both of them for your retrieval tasks. The CLS embedding was used in earlier dense retrieval systems. These are called single vector databases. But recent systems increasingly use multi-vector representations where both the query and the document is represented by the whole bag or a less compressed version of the bag compared to one vector. So both kinds of retrieval tools exist. How would a single vector system work? So suppose there are C documents in the corpus, and each document has been condensed into a D-dimensional real vector, so in R to the D. So the whole corpus is indexed by 1 through C, which I will condense as box bracket C like this. And each vector being D-dimensional, so that's D dimensions. So that Cth document, small c, is this row vector xc. And the whole corpus is this C times D dense matrix. The query, meanwhile, is like another document. So that has also resulted in a D-dimensional column vector, shown in brick red. The similarity score between a document xc and the query q is very frequently defined as their dot product. Or, in case all these vectors have been pre-normalized to have unit L2 norm, you can interchangeably use the cosine of the angle between them and the dot product. Same thing, because their norms are 1. So we can take this matrix X and we multiply it by the vector Q. That way we get C scores, right? Every score here is the inner product between the document and the query vector. So we get C scores. Our goal is not to really compute all the C scores if we can help it. Our goal is to report the K rows in the score vector which have the largest scores. That's what should appear on the first page of your search result. If you do this naively, you'll of course take order CD time to compute the matrix vector product. So the challenge is to spend time that scales very slowly with C, definitely sublinearly, ideally a constant. But some scaling with D and K may be tolerable. Okay? Now, this is all well and good, but it doesn't satisfy certain kinds of retrieval needs. For example, our query is birthday of composer of the film Shruti Layal. Okay. Now, if we retrieve documents using certain standard measures of ranking documents in the dense embedding space, and the documents are scored independently of each other, then the top 3 documents might look like those. And they would have a score of their own, but none of them really answered the question. Right? Each of them matches something important. Shruti Layalu is a relatively rare word, so its occurrence in a document is kind of significant. Despite that, none of them answered the question. Actually, the second one names the composer, but it doesn't have the birth date of the composer. There are other things that might look like birth dates, but they're not related to the composer himself. Okay. In contrast, the gold set comes from the following 2 documents. The first one gives you the composer name of the movie. The second one gives you the birth date. Now observe that there are various kinds of matches here. A deep learning system is smart enough to understand that this is a birthday, like a bracket followed by a date is often a birth date, right? Composer matches with the first document, and the movie name, of course, has a strong match. Now, if the AI-based or whatever, the text encoder has repeatedly seen that Mahadevan is a composer, then Mahadevan vector has some elements of composer in it. So this will also be a partial match. So the way dense systems would ideally fish out multiple documents to answer the query should be like this. If I had to explain to a human why the 2 bulleted documents are collectively answer to this question, I would have to draw these red edges across, and that shows you why the match happens, right? So multiple documents need to collaborate to return the correct response. It's not a competition between documents. That's the new thing we realized through the last couple of years. In traditional top-K retrieval, existing implementation is just try to increase the number of documents they retrieve and hope that everything they need for this cross-document inference will be included in the retrieved set. But this may not work if the top-K documents are redundant with respect to each other. For example, there could be 100 reviews of this movie crowding out the top 10, right? You can keep fetching things with high score, but it's only single documents which do not contain enough to infer the answer. So the top-K paradigm with single document scoring is inherently limited. In fact, in this particular query, if you increase your horizon to 5, you still won't collect both the necessary documents. Okay. So the motivation, I hope, is clear. Another motivation comes from table retrieval. You could have a table like 2 tables, in fact, shown. And again, the answer comes from analyzing and extracting and synthesizing from both tables. The question is, what is the sum of securities loaned in, et cetera, et cetera. So to make it clear to ourselves, I have color-coded spans of the question. And as you can see, all the spans are not satisfied by any single table. Right? The tables contain a lot of extra stuff. And if we had to make a whole document to whole query match score, it would come out to be quite low. Okay? On the other hand, no single table element covers the whole query either, although when a cell is relevant, most of it is relevant to the query. Okay? So there's this bimodal behavior. We kind of lose at both ends. The whole table doesn't match the query because it has extra stuff. Single elements don't match the query because the query wants to connect multiple elements. Okay. So what we need really is a small subset of table elements which collectively cover large colored patches of the question. And existing vector database similarity functions like cosine or L2 distance don't go anywhere near to addressing this problem. It also seems clear at this point that a pooled single vector representation of text is woefully inadequate to address this situation. That's not just our pronouncement. Important people in the field have made strong statements to that effect, that you cannot compress the meaning of a sentence into one vector. One search system a few years back called ColBERT tried to address it by replacing the single pooled representation with a bag of vectors. Bag meaning duplicates are fine, although duplicates rarely happen in nature. So now, a document becomes a capital XC and not a lowercase xc. Why is it uppercase? Because it's a set. It's a set of vectors. If the length of the document is L, every document has L words with padding if required, then the Cth document has vectors XCL. Each vector is now in R to the D. Okay? And the query itself, again, has multiple words, each with its vector. As you saw in the text encoder block diagram, every word is outputting a vector. ColBERT defined the similarity or the score or utility of one document as follows. Take one query vector Qn, small n, out of the capital N query vectors. Qn looks for the most supporting document vector. So it's best partner vector from the document. In other words, max over the document length Qn dot the Lth vector from the document. Okay? So as a picture, think of Q1 through Qn, and here is my Qn. On the other side, you have XC1, etc., XCN, XCN, or L, sorry. Okay. So each queue picks its best partner. Multiple queues can pick one partner in the document, that's allowed. And then you add up the score on these edges. So it's a form of assignment where we don't insist on one-to-one. On the document side, it's allowed to be many. And then you add up these scores, and you get the score of the document. Now you can add or average. It's kind of equivalent because the query is a fixed size, right? It doesn't depend on individual documents. But observe that at the end of the day, we still define the utility score of one document at a time. There's only one small c in there. It's just that the scoring function became a little smarter. Okay? So each document is still required to compete against all the other documents. So at this point in the talk, I'd like to propose to you that thinking of documents as competitors or gladiators is the wrong view of the world. That documents should instead form coalitions to solve the query. So in moving from gladiators to coalitions, the formulation changes as follows. In the gladiator mode, we had C documents. Each capital XC was a bag of vectors, fine. Query Q is assumed to be satisfiable by one document. That's why I'm scoring each document in isolation. Right? And I defined the utility score of a document as S of X sub small c, lowercase c, given the query. And the goal was to find the documents with the k largest score as competing alternatives. In case my top bid is not correct, you can hopefully find your answer at the second. It never says you have to get your answer from numbers 2, 5, and 6 together. On the other side, we have the coalition. We have fine-grained documents, which could be individual sentences, it could be table cells, it could be nodes in a graph. And this text is very fragmented compared to the full document and even a query, as you saw in the table example. No single document can satisfy the full query, so our goal is to find a small set S of documents which collectively achieves large utility. So we have to define a new utility function now. So S is the subset of document IDs that we need to retrieve. So in gladiator mode, my score was sum over query, maximum over document terms or document words. The coalition doesn't have a single document. It chooses a set S. So its utility allows a query vector Q to find a supporter from the union of all word vectors in the coalition. That's all. It's a very simple change. Okay. So the utility of the set given the query is the sum over query vectors, the maximum or the best partner over all x's in the union of all the bags of q dot x. Okay. Now, it's easy to observe that this is a monotone function. Your utility will go up the more documents you fetch, but of course that involves fetching more from the index. That will take more time, and it will also result in lowering your precision, meaning you'll fetch a lot of junk that the user has to sift through. And it's not only a user, it's also known that if you retrieve too much for LLMs in the form of a RAG system, the LLM will get confused with extraneous retrievals also. That's also established. So it's monotone, and it's also submodular, meaning that if I have a small set S contained in a larger set S prime, then the bang for the buck you get in terms of the incremental benefit in utility by adding a S, small s outside would be larger for the smaller set than the larger set. So it's diminishing returns. As the set grows larger, some element outside has less to offer. That's also easy to show. Okay? Now, submodularity means that we can do a greedy approximation. We can choose documents one by one and reach within a constant factor of the optimal value of any set in the corpus. So the next thing we have to define is the marginal gain delta from adding some corpus element to S, which was not there. So C is not initially in S. We are going to add it to S. What's the incremental benefit we are going to get? So the incremental benefit of adding C to S given the query Q is obviously f of S union C minus f of S. The utility with C in minus the utility with C out. Fine? And we can expand out the formulas for f and realize that it's sum over query words f of S union C with regard to Q. So we have, this is Q is in Q minus FSQ, everything inside the sum. Right? And now you see that we expand out the f S union C, and that's the cover of the query vector from C itself versus the cover of the query vector from S. We take the best cover of them, right? We are looking for the best partner. Minus whatever I already got, the coverage that Q already got from the old S. Right? Now note that this max of AB minus B is the same as the hinge function on A minus B. When A is larger, it's A minus B. When B is larger, it is 0. Okay, so that's an important observation, although it's a very trivial one. So now I can rewrite my incremental or marginal gain from adding C as the sum over query terms, the utility of C itself, only C, minus the utility I was getting out of S itself, but with a hinge outside. In words, FCQ is the support from the next candidate document, but if S already provided better support, then it's worth nothing. It's worth 0. And remember, this hinge function looks like this. And that, inside the scoring function, will throw a monkey wrench which we have to fight with a new hashing algorithm. So that's the main content of the talk. So we want to index the document set for successive max marginal gain, greedily. Okay. So we'll grow our output set S one document at a time. We'll start with an empty set S0, and then we'll grow it by one element to one document to S1, and so on until we get K documents in K rounds. In each document, each round we'll add one document which we'll call CK. We will choose CK to maximize this marginal gain. And the problem is that we have to do this where C is in the millions, at least, right? And so we have to do this fast. K rounds, right? So using a ColBERT style probe, we will probe the index, whatever index we build, for every query vector Q, where what we want to do is argmax over candidates not already in the set, the marginal benefit of C, which, as we have seen, is argmax C minus C not in S, FC minus FS plus. I'm just repeating the formulas for convenience. Okay? But unlike ColBERT, the problem is that in ColBERT, there was no such thing as S, right? So this term was not in ColBERT anywhere. So now our problem is that our scoring function for the next document varies as we grow the set S. And we can't afford to de-index everything because that would defeat the purpose. Our index has to be static. We have to somehow adjust the query as we do this, right? The index cannot change, and this is the first hurdle. Changing S must be folded into some kind of lifted query vector, say Q tilde. So the first question is, how are you going to doctor the query vector so that it records within itself the effect of already having covered part of the query? Okay. Yes?
So if I look at the document space, aren't we trying to find, suppose I have a document, I don't want documents very close to this document. I'm looking something which is distant and then maybe distant so that...
So you're saying there's an area of information retrieval for diversity, right?
Yes, kind of.
So diversity in this case would be like an unguided weapon. Just because two documents are diverse doesn't mean they covered the query.
Correct,
right?
yeah, true.
In fact, it's easy to compose examples where if there are lots of documents, so I could make two documents which are very, very diverse.
May not
but which
match,
may not cover
but
the query.
this distance may be, something.
That's
okay.
right. That's right.
Thank you.
Okay. So the nice part is that this utility function is just one real number. And so lifting it to a higher dimensional space is actually quite simple. All we have to do is to extend it with one dimension, in fact. So we take the old document vectors X and we pad it, so this is D dimensions, and this is plus one dimension. So all we need is D plus one dimensions. So I record X and minus one in the vector. On the other side, when I query, I am going to pack the last element with the utility I've already achieved. And then the inner product of those two is going to be exactly q.x minus fsq. Easy peasy, right? The only difficulty remaining is that outside, instead of being a linear thing, there's a plus sitting there. There's a hinge sitting there. And standard metric-based indices don't know how to deal with this hinge. Right? So that's the key challenge here. So the nice part is that Q tilde will just be Q padded with one number, which is the cover I have already obtained for Q. And on the document side, all I have to do is to pad it with a minus one. That takes care of things. So X tilde can be pre-computed and indexed independent of any query, which is the nice property we need. But the next hurdle is this plus, the hinge function. So how do we deal with that? So how do we go from q.x to q.x hinge? The positive value, if any, otherwise 0. Right? So this document ID sets are, so how does ColBERT work in anticipation for what our algorithm will finally look somewhat like? For each query vector Q, ColBERT probes this index. Index returns a bunch of document IDs such that the document C, every document C has some XCL that has a large value of q.xcl. So you could think of ColBERT as really an inverted list, except the keys, instead of being discrete tokens, are actually vectors. Okay. These document ID sets are merged and filtered in various clever ways to funnel down the candidates until things become manageable. But now we need to maximize the hinge function on q.x, not q.x itself. To do that, we'll take a little detour into the foundation of single vector DBs. That will give us the intuition of how to do it. So single vector DBs, many of them in the earlier days at least, worked by projecting the query and the document, single vectors, onto some other third random vector shown in gray, which is W. Okay? So let angle QX be the angle between Q and X. Let's say that Q and X has been pre-normalized to have unit length. And if this is Q, then its perpendicular vector, its perpendicular plane, in this case a straight line, is shown as a dotted line. Similarly, if that is X, this perpendicular shows a dotted line perpendicular to X itself. Now, in this picture of two vectors, one red and one blue, I'll now plant a third vector W, which will keep rotating. Okay? As it rotates, observe carefully what happens to the relative position of the gray hyperplane and the position of the X and Q arrows. Now, before we get started, For unit length, the cosine of the angle between W and X is just W dot X. So if the angle between W and X is acute, less than 90 degrees, then the cosine is positive and the sine of W dot X is +1. If the angle between W and X is more than 90, then the W dot X is negative because the cosine is negative, and the sine of W dot X is -1. Clear? Okay. Same goes for W and Q. W dot X, W dot Q, same thing. So the question we will ask is, as we move W around, X and Q are fixed. As we move W around, what fraction of the time will the sine of W dot Q differ from the sine of W dot X? Okay. So you see this red arrow, which is the Q vector, and its perpendicular hyperplane dotted. You see the blue arrow, and now the gray arrow will start moving around. At this point, both cosines are positive. Both cosines are still positive. As soon as the gray dotted line enters between the two vectors, that is the gray arrow enters the red zone, the gray hyperplane starts dividing up the red and blue, and so the signs start differing. And I thicken the arrow to show that. Okay. While the gray arrow is passing through the red cone, sine of W dot X will be different from sine of W dot Q. One will be +1, one will be -1. Right? Otherwise, it will always be positive. So, the gray vector W must be in the orange cones for the signs to be unequal. And this makes intuitive sense. If the Q and X are very close together, it will be very hard to split them. So almost any W would agree in terms of which side of the gray hyperplane they fell on. Okay. So elsewhere the signs will agree. And therefore, the probability, so suppose instead of now circulating the W's uniformly, I just randomly sample them at uniform between 0 and 2 pi. Story is the same. The probability that the sine of W dot Q differs from the sine of W dot X is 1 minus the angle divided by pi. Why pi? Because I get 2 red sectors out of 360 degrees. Okay. Now, let's verify the extreme conditions. If, suppose Q and X are the same vector. Okay. So, if Q and X are the same vector, sorry, this may be an equal here, right? So, let's see. If Q and X are the same vector, then Q dot, the angle is 0. And so this probability will be 1. That will be the sign agreeing, actually. The sign will always agree. Okay? So we'll fix this as we go along. Let's see if I can switch the slide. Okay. So let's see. So the sign disagreeing means that the vectors are far apart, so this should be equal. If the signs are equal, if it's 0, then yeah, probability will be 1. Okay, signs will always be equal. So now, if we look at how these two functions look, so on one side I have plotted the cosine of the angle between Q and X, that's the cosine curve. On the other side, I have plotted 1 minus Q over angle Q, X divided by pi, and that's this line, right? So ranking using one of them is the same as ranking using the other. You might have to invert the order. And this works in any number of dimensions. So now, let's return to our sub-goal. In our sub-goal, this Q dot X hinge is either Q dot X or it's 0, right? So it's Q dot X if Q dot X is greater than or equal to 0, it's 0 otherwise. Right? So we choose a random unit vector W, and then we define a new feature function where green can be either query or X. And inside I have 2 elements. One is d-dimensional, this is also d-dimensional, and that is also d-dimensional. So this is, the whole thing is 2D dimensional. The first is just a copy of the input. The second is a copy of the input with a plus or minus sign, depending on the vector W. Okay. Now, if you take phi applied to q and then phi applied to x and you multiply them, you will find that because of the 1 over square root of 2, it will become a half. And inside, it will be q here and x in the other one, so q dot x plus the product of the signs and the q dot x again. So this is basically half times q dot x plus minus q dot x. So this is either q dot x or it's 0, depending on whether the signs agree or not. Okay. Modulo the technical details is the only message that needs to stick, right? So basically I'm choosing between two values q dot x and 0 with probabilities depending on whether the signs agree or not. Now, as you know, the probability that the signs agree is 1 minus q dot x over pi. Okay. Sorry about that sign flip earlier, okay, as before, right? So if qx approaches 0, then this probability approaches 1. Right? And in that case, if the angle is small, if the angle is acute, then I'll take that option, which is the correct thing to do. Right? So in case the angle is acute, that means q dot x is positive and q dot x hinge is q dot x. Probability that the sign agrees is 1 minus the angle divided by pi, and because the angle is less than pi over 2, this is more than half. And therefore, the probability that the product of the feature vectors will be actually the hinge is more than half. So we win in case things are acute. That we already knew, because if it's acute, then the hinge function doesn't do anything. On the other side, if the angle is obtuse, then the angle is between pi over 2 and pi. In that case, q dot x is negative and hinge of q dot x is 0. So now the probability that the signs agree will be 1 minus qx over pi, which will be less than half. And therefore, the probability that this product of feature vector will be 0 will be more than half. So we win in both cases. Okay. So this we can now amplify by sampling not 1, but r copies of the w vector. And it also stands, and you can easily figure it out, that if there exists a w which will make this happen, then the maximum of them will make it happen. Because there's nothing bigger you can get. Okay. So the probability that the maximum over these r replicas will fail to compute the hinge loss will be less than 2 to the power minus r. So we'll rapidly make it almost sure that we are computing the correct hinge function on the dot product. Okay. So therefore, given the query, we will start with an empty set S0, and then in every round, for every query word, we will compute this q hats or q tildes. We will probe the indices, merge and prune, and then we'll combine. So that's the broad architecture. And here is the scary diagram which shows the whole system thing. During indexing, we produce R replicas of the index. And during query time, every Q that comes in will probe each of them. Right? This index fans out to all the R indices. Those are merged. And then finally, I get my SK at the output. There's a whole bunch of baselines. I don't have time to describe all possible baselines here. But how do these things work in practice? So the most interesting thing to plot is how quickly can you get high set utility. Like with time, how quickly does the utility function f grow with k, right? So if you did exact greedy computation over the whole corpus, of course you'll get the maximum possible benefit, but that's totally impractical, it's very, very slow. We will compare other methods based on the coverage score that we actually get, FSK given Q, versus what we call efficiency. Efficiency is the time taken by this slow algorithm, exact greedy, divided by the time taken by other faster methods. And if the number is larger, that means my method is very fast. So this is what you see. The older methods like, the exhaustive methods like lazy greedy or exact greedy, those are all here. So their utility is very high, but their efficiency is low. Near 1, they're taking as much time as exhaustive search over the corpus. There are some newer algorithms like Moveda and Warp from Google or DeepMind, and there's Played from someone else. So those are far more efficient. Those are 4 orders of magnitude faster in terms of query execution time, but their utility drops, right? Some of them have very low utility, like Moveda, Whereas our method is this black curve, which provides some kind of a Pareto frontier. We are 2 to 3 orders of magnitude faster than exhaustive search, but we are higher than anything else which doesn't do exhaustive search. Okay. Same is the case with another data set. Now, the second thing to ask is, we set out on this path saying for question answering, we need to retrieve a subset of passages until we can answer the question. That means we need to get the last of the gold passages. We need to capture all the relevant passages in our top K. So what is the K we need to capture all the relevant documents needed to infer or answer the question by various systems? So here we see that both Hotpot QA and 2Wiki multi-hop QA, these are two popular question answering data sets, where you need to assemble you see that by how low the initial bars are and how high the later bars are. Because you keep finding the gold document or passage until rank 5, 6, etc. Whereas our system can basically get everything we need within rank 2 or within rank 3, and then we don't need any of the other ranks to collect the remaining documents. Again, the same story here. The faster methods, these three are the faster methods, they miss a lot of things at rank 1, they try to make up later, whereas we get almost all the good ones at ranks 2 and 3. Okay? And we get it much faster, as you saw from the previous slide. Right? So we get it with very high efficiency. How about the impact of the number of replicas? You might be feeling a little unsafe saying, oh, we are doing this with this randomly sampled vectors W. How reliable is this story? And we have seen some analysis that is like probability of failure goes down as 2 to the power minus R. But in practice, how well does that work? So here you see that we plot K again. And the y-axis is again the utility we collect with every passing K. And you can see that as R increases, we quickly achieve optimality saturation. So you could look at collective search also in other settings, and we have done a great deal of that. For example, you could look at it as subgraph matching. So if I ask birthplace of a cricketer who led the winning team in Adelaide in 2003, you might want to compile that into a graph like this with certain nodes which are unbound variables which you want to bind to actual ground constants. Meanwhile, there could be corpus text like this which give you part of the answer again. And there could be web pages listing victories and defeats of various cricket teams in various matches. All these can be turned into a uniform graph representation. But you can really prove you have gotten an answer only if you start linking them up, saying Indian cricket team, there is India over there. This victory corresponds to this row in the table. That E1 is Kolkata, and that E2 is Saurav Ganguly, and so on. Right? And that cricketer, this is the birthplace, and so on. So the foundation of this kind of matching is subgraph isomorphism, which means if I have a graph GQ, and I want GQ to be the subgraph of GC, then wherever there is an edge here, there needs to be an edge there. Okay? But it's possible that there is no edge here, but there's an edge here. That's allowed. So it's one-sided. Okay? So what we are looking for is that there's an adjacency matrix AQ, which needs to be element-wise less than or equal to AC. So AC has edges between 2 and 3, 2 and 3, and AQ does not. That's okay. So this is a essentially asymmetric scoring function, and it's also a computationally hard problem. And we asked, can neural graph representations help in real data sets? And we had a series of papers outlining whether you can detect neurally if one graph is a subgraph of the other. Can you estimate the size of a maximal click in a graph? Can you compute edit distance between two graphs? And can you use that for efficient indexing as well? We have also done some recent work on going back to our roots in terms of sparse inverted indices, which are extremely efficient. They have been optimized for over 20 years, and they are much faster compared to any dense vector database. So can we take our embedded artifacts like graphs and map them to fake documents with fake words so that they look like traditional text documents, and then let a sparse indexing system index them? There are many other intriguing retrieval problems. I won't have time for that. So we are in a new age of dense retrieval and vector DBs. Compression to a single vector is easy, but it's lossy. real applications benefit from composite abstractions. This is not just one vector. This could be a set of vectors. It could be a sequence of vectors, graphs, other data structures where everything has to be vectorized properly. Distances and similarities that are faithful to applications are difficult to algorithmically index for. And that's the essential conflict between them. And we have these great challenges at the confluence of machine learning and algorithms and practice. So someone might have said, ask not what LLMs can do for you, ask what you can do for LLMs. The picture is a bit wrong. That's the right picture. So that's the end of my talk. Thanks for your attention. I'd be happy to take any questions.
Okay. Thanks a lot, Professor Chakrabarti. Questions? We have time for questions. Please.
Sir, it was a great lecture. It was very insightful hearing you speak. I just want to ask you, sir. Very recently, we're seeing like LLMs are being used very frequently as re-rankers and judges, especially in the field of information retrieval. And we see models such as RankZephyr and RankLlama and so forth coming up. And these are increasingly being used, especially in the second stage retrieval,
yes.
Two-stage retrieval pipelines, essentially. I just wanted to ask you, Professor, how far are we in the domain of IR that these LLMs be procedurally more and more used in these pipelines, especially considering right now, mostly in initial phase pipelines, BM25 split, etc. is being used as usual. And then in the next stages, we are using RankZephyr, Rank, etc. And then apart from, we are also moving on a little bit from algorithms such as MonoT5, DuoT5, and so forth, onto these LLM re-rankers. So how far do you see this is going to, and how do you think this is going to shape and impact the future of information retrieval? Thank you.
Right, so LLMs as re-rankers are quite good. It's one of the places where they should be used. Right? The couple of points. One is that if you have lost recall in the first stage, then nothing can save you. And this work was mostly about first stage recall. Right? So that problem remains. The second is that LLMs, which are not really LLMs, so SLMs are actually great at doing re-ranking too, okay, particularly with a little bit of domain-specific training. Again, that's how they should be used. In particular, if you have ranking tasks where you want to remove redundancies, like LLMs may already be fairly good given 200 things to output 10 diverse things. Right? They're also good at linking up the different things you have fetched, particularly in this setting of coalitions, and then making inferences across it. You just need to give it the raw material to work on. The flip side is that those second stage re-rankers are inherently slower, right? And they need long context. They need to be either trained away or other interesting devices have to be found to make them less sensitive to ordering effects, like the lost in the middle kind of problem. So you need to fight those a bit. If your first stage retriever does a reasonably good job, then many of those problems should be possible to handle. One area where re-rankers may be explored a bit more is, say, connections between abstract types in the query and concrete things in the answer. Like I want the birthplace of a cricketer. LLMs can tie up birthplace to a particular city name or a country name, but that's a bit incidental, right? So how well does the LLM integrate into this query solving process that Kolkata is a birthplace or can be a birthplace? So this won't be missed for head queries, but it might be missed for tail queries. It won't be missed for anything like a city, but it might be missed for a particular phone brand, which is relatively new because training data in the LLM is very scant. So I think this matter of language integrated with instance of, part of relations is pretty important for question answering, because if you think about it, most questions are where you don't know some aspect of the world and you're trying to find out, but you can coarsen it, right? So you can say, who discovered penicillin? And you're implicitly asking for someone who feels like a medical doctor, a chemist, a biotech person, right? Whereas if you change the sentence to, by one word, who discovered Antarctica, you're looking for an entirely different kind of person. It's not difficult to infer that you're looking for a certain kind of person. But unless you're asking for such famous things as penicillin and Antarctica, if you're asking for lesser things, then it's easy for LLMs to miss recent information where that particular bioscientist has been only mentioned 10 times. It may not know. Particularly if their names collide with some famous cricketer, then you're toast. Right? So that needs to be fixed a bit. Canonicalization is missing. Cross-passage linking, which takes canonicalization into account, is missing. There are a few things missing there.
Yeah, so what kind of conditions would guarantee that you would require only a small number of documents to cover the entire query?
Yeah, that's a great question. So there could be aggregative queries asking about how many ponds are there in Brazil or something like that. For it, you may need to bring in hundreds of documents. So yeah, you're exactly right. The hope is that such large aggregative questions are not also complicated join questions. If both happen, then the only recourse we have at the moment is to have like a LLM be a planner for access to a knowledge graph, and then do aggregates using a tool, and then hope that you can throw this under a passing RL and it will take care of your misery, so that sort of thing. Yeah.
Professor, thanks for the presentation. To be honest, I did not fully understand your research, but one practical question from my point of view, from a practitioner point of view. I am a software tech entrepreneur building a graph and vector database. When we look at vector algorithms, vector-based algorithms and graph-based algorithms, one thing that I see is that when you have to build a vector database, you are essentially pulling out all information available in the documents. You can't miss out any information, which means that you really have to kind of boil the ocean. Instead, if you have an opinionated parsing of the document and build out named entity-based graphs where you maintain the relationships, what we are trying as a practitioner's approach is that you extract named entities and relationships in an opinionated manner, build out a graph, combine it with a vector database so that you have graph algorithms at your disposal and also vector retrieval at your disposal. Do you see this as more viable for commercial applications, or how do you see this from your point of view?
Yeah, this form of architecture is actually quite dear to me. The difficulty is you need to reach certain threshold of accuracy in extraction and accuracy in canonicalization until it starts paying. Public benchmarks rarely show big benefits of this. And there's this systems like GraphRag which try to do this kind of thing, right? What would be interesting is to put them to stress tests by saying, I want my retrieval from a private knowledge graph and private documents, but then the LLM brings in a lot of public knowledge pollution into the mix. And now let's see if it's good enough to separate the two or deal with it properly. So I have a John Smith inside my company, but there are 2 million John Smiths outside, right? So, yeah. Or to a more made in India example is, if you look at the customer records of State Bank of India, you might actually find a dozen Amitabh Bachchans who might even do a fixed deposit.
Right.
So a LLM coming in from outside shouldn't dissuade SBI from pitching FDs to them.
Right.
Yeah.
So do you see this as useful for future?
Oh yeah. I think it's quite worthy pursuing for them.
Thank you.
I actually have one on top of that. So first comment is that I have seen Narendra Modi in the SIR, the election database, so the names are generally disambiguated. But that's a comment. But my question was that, so it actually felt, and just guessing, it actually felt a little bit like you're building a knowledge graph and inferring the edges of that knowledge graph and then running search on it. So is that something which is you're doing? And if you are, then do you see using graph neural networks for actually retrieving the documents better in the neighborhood? Because if the knowledge graph is perfect, then they should be in the 1 or 2 up neighborhood of where do you start from, even partially. So do you have any thoughts on that?
So curated knowledge graphs are extremely incomplete, right? So you cannot really depend on them. I'm not sure I caught the second part of your comment. So you're saying, why don't I do a graph expansion-based retrieval, or?
Right, so it was a follow of the first comment. So whether what you're doing can be termed as, inferring that knowledge graph, which is not curated, but you are just getting those relationships and using graph isomorphism, actually predicting the edges. And a follow-up on that, if you have a better, more complete graph built in this way, would you see using graph neural networks for better retrieval?
Well, GNNs have a host of problems of their own, right? They're especially oversmooth, and a fixed number of layers is just not the right solution. You need very diverse number of layers in diverse areas of the graph, right? So there's this Monty Python joke about how to lob a grenade, right? So you'll count to 5, you'll not count to 4, you'll not count to 6. So GNN layers are like that. You go one layer below, you go one layer above, everything falls apart, right? So you don't want that. So there are severe problems, right? So I would rather think about it as we need certain other kinds of graph networks, which ideally should be message passing in nature for scalability, but they need not be current forms of GNNs. If you read the old literature on, say, PageRank, there are all kinds of fun ways in which you can write PageRank in asynchronous ways so that you are not wasting time doing matrix vector multiplies all the time. So maybe borrowing something from there.
Thank you. So let's close the session, thanking the speaker now.
Thank you.